Most of us build our lives on relatively flat ground. We lay roads, pour concrete, and navigate a horizontal world. But travel far enough, and that stable horizon violently shoots upward into massive walls of rock. These physical features, what geologists call landforms, appear permanent to us. We map them and name them, assuming they've always been there. But the Earth's surface is constantly shifting. Right now, an invisible war is tearing across the globe. On the outside, exogenic forces like wind, water, and glacial ice are grinding the surface down. But deep underground, endogenic forces, driven by intense heat and pressure, are aggressively pushing it back up. When those internal forces win, they create massive physical obstacles. These heights force moist air to rise and cool, creating heavy rain on one side and dry deserts on the other, while their frozen summits serve as the slow-release headwaters for the world's largest river systems. To understand how these giants rise, we have to look below the surface. Earth's crust exists as a series of massive, interlocking tectonic plates, all floating on a churning layer of superheated rock. When two of these massive plates drift into each other, they don't bounce off, they lock together in a slow-motion car crash. As the immense pressure builds, the crust physically crumples and folds upward. Because this happens over millions of years, the rock doesn't shatter like glass. Under that kind of sustained heat and pressure, it behaves almost like a fluid, bending and warping as it rises into the sky. This impossibly slow, violent subterranean collision lifts entire continents, building the foundation for the highest peaks on Earth. Geologists categorize these structures into 3 specific blueprints based on how they were built. The first is a fold mountain. Like pushing the edges of a thick notebook toward the center, the Earth's crust buckles and waves under lateral pressure. This is exactly what happened when the Indian tectonic plate smashed into the Eurasian plate, rippling the rock upward to form the Himalayas. The second blueprint relies on cracking rather than folding. Sometimes the crust fractures along fault lines. As internal pressure builds, massive chunks of rock are forced straight up, while neighboring sections drop down, creating giant, uneven stairs. These are block mountains. You can see this stark elevation change in places like the Sierra Nevada, where an enormous block of granite was tilted and pushed thousands of feet above the surrounding valleys. The final blueprint is built from the inside out. During an eruption, liquid magma escapes from deep underground, cools into solid rock on the surface, and gradually stacks up over thousands of millennia. Because the molten rock often flows out evenly in all directions before hardening, these volcanic mountains frequently form striking, perfectly symmetrical cones, like Mount Fuji. Whether they are folded, faulted, or erupted, the specific geological mechanism that built a mountain ultimately dictates its steepness, its altitude, and the extreme conditions that life will face upon it. So once these giants are pushed into the sky, how does their sheer physical height alter the environment around them? This diagram illustrates a strict rule of climatology. As elevation increases, the air thins out and loses its ability to hold heat. For every 1,000 meters you climb, the temperature steadily drops. Eventually, you reach a specific altitude where the temperature falls permanently below freezing. This threshold is called the snow line. Above this point, the forests disappear, leaving only bare rock, thin air, and year-round ice. You might assume that permanent snow is reserved for the extreme northern or southern latitudes, but Mount Kilimanjaro sits in Tanzania, mere degrees from the blazing heat of the equator. At nearly 6,000 meters tall, Kilimanjaro proves that altitude defeats latitude. The African heat at its base simply cannot reach the summit, allowing a freezing, snow-covered peak to loom directly over a tropical landscape. By trapping cold air high in the sky, mountains act as vertical climate zones, forcing plants, animals, and humans to adapt to freezing, oxygen-deprived conditions. Living in these zones requires intense physical adaptation. But how do human communities manage to farm or build on these steep, unstable angles? The answer is an ingenious architectural solution known as terrace farming. Instead of fighting the slope, farmers carve the hillside into flat horizontal steps. This creates level ground for crops to take root, while acting as a physical barrier that stops topsoil and rainwater from washing down the mountain. To survive in this environment, human beings cannot simply endure the landscape. They have to physically reshape the contours of the rock to create sustainable lifelines. Yet, even with that level of engineering, living on a mountain comes with unpredictable risks, driven by the constant pull of gravity. High-altitude slopes frequently suffer avalanches. When heavy snowfall accumulates, a shift in the wind or a slight disturbance can cause the entire snowpack to shear, sending a massive, rapid downfall of ice and rock tumbling into the valleys below. At lower elevations, heavy rains or minor earthquakes can destabilize the earth itself. This triggers landslides, where violent collapses of soil and debris instantly wipe out roads, forests, and infrastructure. The exact same steep slopes that make these peaks majestic also make them inherently volatile, demanding constant vigilance from the people who call them home. Mountains function as active, evolving systems, powered by the intense heat of the Earth's interior. They dictate global weather patterns, isolate unique ecosystems, and force humanity to apply its greatest ingenuity just to survive on their slopes. From the lichens clinging to the highest rocks to the farmers carving the lower slopes, life here represents a series of highly specialized adaptations to the planet's thinnest air and steepest angles. By understanding the unseen subterranean forces that build them, we gain a much clearer picture of the incredible, living planet beneath our feet.